Now let's talk about the implementation of a hash map. Now, most likely you'll probably not be asked to actually implement a hash map in an interview. It's pretty rare that you have to do that. And the implementation of hash maps can get really, really complicated. We'll be talking about the general concepts, and then we'll be coding up a relatively simple hash map. But I think the concepts are what you should really focus on, because the concept of hashing and the other ideas we're going to be talking about definitely come up in software in general. So this is definitely not the last time you're going to be hearing about these ideas of hashing, key value pairs, and things like that. First of all, under the hood, a hash map is actually implemented with an array. So in this case, we'll have some index, and that index will be mapped to the key value pair. And just because we have an empty hash map right now does not mean the size of our array is zeroed. Even an empty hash map is going to be non-zero. In this case, let's say we have an empty hash map, but our array is of size 2. We have index 0 and index 1. Now, the actual key value pair in this case, suppose it's just null, right? Some kind of default value, it's empty. We're basically indicating that we don't actually have anything stored here just yet. Now, with an empty hash map, the first thing we would probably want to do is start inserting some values. But how does an insertion actually work? In this case, let's say we're calling it put. It could be called insert or something like that. In this case, the key value is going to be a string, and the value itself is also going to be a string. That doesn't necessarily have to be the case. This could be an integer, or this could be an integer, or they could be some other type. It could actually even be an object. But what's important here is that we have a way to convert the key. We don't care so much about the value, but the key should be able to be converted into an integer. And how we're going to do that is called hashing. We're going to have some kind of hashing function, which is going to take the key value and then convert it into an integer. And when we have that mapping, you can see where I'm going. We're going to use that integer as the index, and that's how we're going to decide where to put that pair, that key value pair, into our array. So in this case, this array is actually an array of objects where the object itself is a pair, a key value pair. Well, the simplest thing would be able to map each character to some integer. For example, the first character A could be mapped to 0. I think L is the 12th character, so that could be mapped to the integer 11, and we could do that for every single character, and then we would add them up, and we would get some big integer. Let's just assume that the integer we get is a 25. I'm just making that up, but the idea is that we converted each character to an integer, then added them all up, and we got another integer, 25. Now, the only problem here is our array is only of size 2, so this is not really a valid index for our array. How can we fix that? Well, this is where a little bit of math is going to come in. We can take any integer, no matter how big it is, as long as it's positive, and we can take it and then mod it by the size of our array. So in this case, mod it by 2. If you're not familiar with modding, we're basically dividing 25 by 2, and we're getting the remainder that's left over. So in this case, 24 divided by 2 would equal 12 with a remainder of 1, because 2 can keep fitting into 25 until we get to 24. And then if we add a 2, we're going to get to 26. So that's too big. With 24, we have a remainder of 1 left over. Now, if we instead of 25, we actually had 24 and we were modding it by 2, then we would have a remainder of 0, because 2 does fit into 24 perfectly 12 times, and then we're left with a remainder of 0. And those are really the only two possibilities. But what's important to notice here is that when you mod by the length of the array, no matter what integer you're modding, you're always going to get a valid index as the output. The result that we get would always be a valid index if we're modding by the size of the array, which in this case is 2. It could have been 3, it could have been 4, but the mod is always going to result in a valid index. And the reason behind that is pretty simple. No matter what integer we're modding by, it could have been 5, the result, the remainder, is always going to be less than 5 because the remainder always has to be less than 5. It always has to be less than the number we're modding by, because if it wasn't, then it wouldn't really make any sense, right? We can't say 25 modded by 5 is equal to 5 because we can still divide this by 5 and then get 0, right? So it's just a little bit of math, but that's the main idea. So we mod by the size of the array to convert any integer like 25 to a valid index. So modding this by 2 in this case would lead to 1. So then we'd say Alice is going to be inserted at index 1. So in this case, Alice is going to be at index 1. The key is going to be Alice, and the value is going to be the city that she lives in, which let's say is New York City in this case. Now we're going to insert a couple more values, but suppose we wanted to first get Alice. We could do that in O of 1 time. We call get on Alice. We would, using our exact same hashing function, take Alice, convert it to an integer. Let's say again it's 25, mod that by 2, then we get 1. So in constant time, we were able to get the index that Alice is stored at. Then over here, we could go to that index and then say, okay, what city does Alice live in again? Well, it's New York City. So that's the idea. And that's why it's so efficient. Now, we're going to run into a few problems though. Let's say we now want to add Brad to the hash map. Let's say we convert Brad to some integer, right? Taking the sum of the characters. And by the way, when we actually convert a character to an integer, most likely we're going to be using the ASCII representation of the character. There are more complicated ones, but if you're using a set of 128 characters, so if we had a relatively small alphabet size, we could do this. Basically, it's a way of converting each character into a integer. And in that case, capital letters are actually different than lowercase letters. Like for example, capital B could be evaluated to like 70, lowercase b could be something like 44. But that's not so important. Let's just assume that we have a way to convert each character to some integer. But let's say we took Brad and the integer that it turned out to be was 27. Now we mod this by 2, we get 1 again. So what are we going to do? We're going to say, okay, at index 1, let's insert Brad. But Alice is already at index 1, so we can't really do that without losing the information we've already stored. This is a problem, and this is the problem with pretty much all hashing. It's something that you can't entirely avoid. It's called a collision. Clearly, it's bad to have collisions, but there are ways that we can work around it. We can minimize collisions and we can try to work around them, but we can't entirely get rid of them. That's really important to know. Hashing collisions pretty much always happen. Now, first, let's understand how we can try to minimize collisions. There's sort of a problem here. No matter what we convert Brad into, no matter what integer it gets converted to, modding it by 2 is either going to lead to a 0 or a 1. If our hash map is half full, like one of the spots is already taken, we basically have a 50-50 chance of having a collision or getting the position that's empty. Those aren't great odds. So typically what happens with hash maps is we keep track of the size of the array and we keep track of how many keys are actually inserted into the array. In this case, the size of the array is 2, and we only have 1 key actually inserted in the array. So we say that the hash map is half full. And typically when it becomes half full is when we resize the array. And resizing the array actually works pretty much exactly the same as when we did it with dynamic arrays, meaning we take the size and roughly double it. And we would have done that not at the time that we're inserting Brad. We would have done that as soon as we inserted Alice. We inserted Alice and then we realized our hash map is half full. So at that point, we would have resized the array. We would have doubled it roughly. So the array would now have index 2 and index 3. So 4 elements now. But ignoring Brad for a few more seconds, what if now we try to get Alice? Well, we convert Alice to the integer 25. We mod it now. Instead of modding it by 2, we're actually going to mod by the size, which is 4. And it turns out that the index is 1 again. So we see that, okay, Alice is still in the correct spot. In this case, it works out, but it's not always going to work out. For example, what if instead of Alice being a 25 was a 27? In that case, when we mod it by 2, it would have gone at index 1, exactly where it's still at. But then when we resize and we try to get Alice again, we try to search for it, we mod this by 4 now because the size has increased, and modding 27 by 4 leads us to 3. So we would say, okay, Alice is probably at index 3. We would check and we'd see that no, Alice is not there. What I'm saying here is when we resize the array, we can't just leave the values where they previously were because the size changed. Therefore, the index using our hashing function might have also changed. So what we have to do when we resize, we take every single key that's already in the hash map, we recompute the hash of it using the new size, and then move it to where it should now be. For Alice's case, 25 modded by 4 is still 1, so it can stay where it is. But if it wasn't, we would have to move Alice to the new position. By the way, we call this process of increasing the array size and then moving all the elements to their new position, we call that rehashing the array. And since we're doing it when the size is half full and we're doubling it every time, it's still relatively efficient because it's going to be infrequent that we have to do this rehashing. Obviously, it's pretty expensive because we're going to have to go through every key that's in our hash map. But as long as we double it the same way that we did with a dynamic array, it's going to be relatively efficient in the average case. So now finally, let's get back to Brad. Instead of modding it by 2, now that our hash map is size 4, we're going to be modding this by 4. 27 modded by 4 is 3. So in this case, we don't have a collision. And it makes sense because our chances of a collision have definitely decreased. We have a bunch more empty positions. So Brad is going to go over here, and the city that Brad lives in is Chicago. And since once again our hash map is half full, we're going to again resize it. So we would double the size. So now it would be of size 8. I'm not going to draw out the whole thing because it's not super important, but let's just assume that the size of this has now become 8. This will help us minimize the chance of a collision, but we're going to insert one more person now, Colin. Let's assume that after hashing the name Colin, we get an integer value of 33. We mod that by the size of our array now, which is 8. We mod that by 8. We get a remainder of 1. So even though we tried to minimize the chance of a collision, which is good, sometimes we still run into the case where we have a collision. We are going to insert Brad or Colin at index 1, even though Alice is already there. And by the way, when we resized this from 4 to 8, we would have actually had to recompute the position for each of these and then potentially moved it to that position. So for Alice, since I think Alice was 25, that was the hash of Alice, and then we'd have to mod it by 8, which in this case would have been 1 once again. So Alice actually would have stayed exactly where they are. The hash of Brad was 27. We would mod that by 8, and that actually would have also been 3, exactly where it still is. That's mainly just a coincidence, to be honest. I didn't even plan that, but it's convenient for us because we don't have to redraw this now. How would we actually handle this now? I mean, if we really wanted to, we could resize the array and maybe that would decrease the chance of this being a collision, but it still might end up being a collision. So we need a different way of handling collisions, and there are actually multiple ways of doing that. One way of doing it is actually at every index, instead of just storing a single pair, we actually store a linked list of pairs. So we could actually have multiple pairs occupying the same index. Now, the downside of that approach is we have to kind of maintain that memory and the pointers and all that. And when we actually run the get operation and we arrive at, let's say, index 1, we're looking for Colin, we would first see in the linked list, we'd have to traverse through the entire linked list. We'd first see Alice is there. That's not who we're looking for. We'd go to the next position in our linked list, and then we'd see, oh, Colin is over here. and then we'd return whatever value we're storing for Colin, which in this case is Seattle. But that's kind of the downside of, and that linked list approach is commonly referred to as chaining. There's another approach called open addressing, and it's called that because we kind of loosely define the position that a key should go at, like the index it should go at. Even though we computed the index 1 for Colin, we don't have to put it here. We can say, well, this is already occupied. Let's try the next position. So we take that index 1 and add 1 to it. So we try index 2. Is this empty? In this case, it is. So we can go ahead and put Colin over here and the city that they live in, C for short. Now, in this case, when we run get on Colin, we're looking for Colin. What city does Colin live in? We would compute the hash 33 mod by 8. We would again get 1. We would see, well, this is not where Colin is. So if Colin exists, maybe they're at the next index. Maybe we open addressed this. So let's try the next index. We look at the key. Well, this is the same key we were looking for, Colin. So we found him, and the city he lives in is Seattle. Now, possibly we weren't looking for Colin. We were looking for somebody else named Dylan, who actually does not exist in the hash map. Maybe we somehow computed the exact same index for Dylan. We would look at index 1. We'd see this is not Dylan. We would open address. We would try the next available address. Is Dylan over here? No, they're not. We'd try the next available address. Is Dylan over here? Nope. Is Dylan over here? Nope. And at this point, we know we can stop. We don't have to search through the entire index. First of all, that wouldn't be efficient. That would be O of n, and we definitely don't want to do that. But we know that if Dylan did exist, the hash of Dylan would be at 1, but this was occupied. So we would have put Dylan over here, but Dylan was not over there. So then we would have tried the next position. Dylan would have been inserted over here, but he's not there. And then we would have tried the next position over here. But this is empty. So if Dylan existed, he would have been here, but he's not. Therefore, Dylan does not exist in our hash map. This will make a little more sense if I explain how we would insert Dylan. So let's say instead of getting Dylan, we're inserting Dylan. Let's say hashing Dylan, we got the index 1. Then we try to insert Dylan over here. Well, this is occupied. So now we try the next available index. This is occupied. Next available. This is occupied. Next available. Well, we're going to insert Dylan over here and whatever city that they happen to live at. So this is a sort of naive way of doing open addressing because we're just trying the next available position every single time. The downside of this approach is we're going to cluster the hash map potentially. If we have a really big hash map and we get a lot of collisions, all the keys are going to be stored close to each other. There are better ways of doing this open addressing. Instead of just computing the +1, maybe we take that value and square it and do other things with it. But the important thing to focus on here is that we have collisions and we have ways of handling those collisions. And there are, more optimal ways of handling that. And you could spend a lot of time learning about that. It's pretty math heavy, to be honest. So we won't go too in depth into it. And you likely won't need that kind of knowledge for coding interviews. But it's important to know that there are ways of handling things like this. Now, the last thing I want to mention before we actually take a look at a simple code implementation of a hash map is that when we maintain the size of the array, it's more optimal for the size to actually be a prime number. For math reasons, that ends up resulting in less collisions for the hash map. So typically, the size of the array is going to be a prime number. So instead of this being 8, it would actually be better for the size to be 7. And then instead of actually doubling this to be 14, because 14 is not a prime number, we would actually, just try to find the next available prime number. Let's say it's 17 in this case, and we would roughly double this, but roughly double it to a number that is prime. So maybe the next one would be something like 37, if that's prime. I'm not even 100% sure, but that's the main idea. Now, this is kind of complicated to implement this in code, So I won't be doing that, and it's very rare you'd actually be asked to implement a hash map like this. I mean, if you're asked to implement a hash map and you have to do it so perfectly where the size of it is prime and you're doing all these kind of crazy optimizations, that would be a very, very long interview question, and it's very unlikely you'll be asked that. Even if you are asked to implement a hash map, it's probably okay to do it a very simple way. That's why I'm going to be showing you the simple way to do it right now. So first, let's look at how we would kind of initialize our hash map. Like I said, we're actually going to be storing pairs in this array. This is one way to implement that. We have like a class, and that class will store two values, the key and the value of that pair. You know, in our case, we were doing strings, but these could be any kind of type as long as you have a way of hashing the key. And this implementation will mostly focus on if we had strings as keys and strings as values. So initializing our hash map, this is Python, but of course you could implement this with any language. The logic will be pretty similar. We're going to initialize the size of the hash map. The size is the actual number of keys in our hash map. Initially, that's going to be set to 0. We're also going to initialize the capacity. I'm arbitrarily setting this to 2, but it could be any number. Optimally, it should be a prime number, but in this case, it's 2, just like we kind of started with in the example. And then our map itself, remember, it's maintained as an array, and in this case, there's only 2 values, remember, and to indicate that it's empty, I'm initializing the 2 values as null. If they were non-empty, we would have some pair for those values. The next really important thing for a hash map is to have some hashing function. Given some key, we should be able to convert it into an integer that fits within the boundaries of our array. In this case, it's size 2, so it should fit in our array of size 2. Assuming the key is a string, we go through every single character in the key and we convert that character to some integer. This in Python will convert it into the ASCII value of the character, but that's not super important. As long as we have a way of converting the character to some integer, we're going to take that integer and just sum all of them up. So initially our index is going to be 0. We're just going to keep adding that integer to our index. We could have some really big integer. It could be out of bounds of our capacity. So what we're going to do before we return is mod it by the capacity. So if our index ended up being something like 10, we would mod it by our capacity, which is 2, we would get 0. If our index is actually not out of bounds, for example, maybe it's 1, we would mod that by 2, and we would still end up getting 1, which is still in bounds anyway. So if it's in bounds, that's okay. If it goes out of bounds, then we'll mod it to bring it within bounds. So by the time we return the integer for this hashing, it will be some index that is in bounds of our array. Now let's move on. So first, let's look at searching for a key, aka the get operation. So given some key, we want to return the value of that key if it exists. If it doesn't exist, we can return null, or we could throw an exception, or we could do something, but the details aren't super important. We care mostly about the logic. So first, we're going to convert that key into an index using the hashing function we talked about a second ago. And then we're going to loop. This implementation, by the way, is assuming we're doing open addressing, where if we find a collision, we're just going to try the next index. So given that index, first we're going to check, is it non-null? Suppose we're searching for Alice and we get an index of 1. We would look here, it's non-null. So then we would check, is the key of what we're storing here of that pair equal to the key that we're searching for? In this case, it's Alice. What we can do is just return that value. We found what we're looking for. But maybe we're actually looking for somebody named Colin. In that case, we would have not found what we're looking for. This is not Colin. So instead, we would have not returned. We would have incremented our index, right? Try the next index. And here, the reason why we're modding by the capacity is assume that actually this part of our array didn't exist. We're looking for Colin. We took 1 and incremented it by 1. Well, that took us out of bounds. To bring us back in bounds, we can mod the index by the capacity, just like we were doing earlier. That would bring us up to index 0. Now we're still looking for Colin. We execute the loop, but at this point, we see that there's null here. This is empty. That means if Colin existed in the hash map, he would have been here, but he's not. Therefore, we know he doesn't exist, and our loop stops. We can return null, or we can throw an exception. We can somehow indicate that the key Colin does not exist in the hash map. Now let's insert into the hash map, aka put. We pass in some key and some value. We want to insert that into the hash map. The idea is similar. We convert the key to some index, and then we start looping. We're looping while true because at any point that one of these executes, we're going to return immediately anyway. So this is just kind of a convenient way that I like to write it. So there's two possibilities. One, that this key does not exist in the hash map. Let's say we're trying to insert Colin. The index we computed was 1. Our loop would execute like this. First, we would check, is this index empty? It's not empty. If it was, then we would insert Colin over here, but it's not. Then we'd execute the else if case. Else if the key of this is already equal to Colin, in that case, we would just overwrite it. But this is not Colin. This is Alice. So then neither of these execute. We just increment the index by 1 and modding it to make sure it stays in bounds. So then we would try this index and we would go back to our loop. We would see that this index is actually empty. So what we can do is create a new pair for Colin and whatever value Colin has, assign it to this index, increment the size by 1. And this is important. Remember, if the size is greater than or equal to the capacity, we are going to call our rehash function, which I'm going to show you in just a second. And after we do that, then we can go ahead and return. Now, assuming we were inserting Alice and we wanted to change her city from New York City to something else, then the else case would have executed. We would have found Alice is already here. We would just simply overwrite the value. We don't have to increment the size by 1 because we're not adding anything. We're just overwriting the value, and then we could return immediately. So lastly, let's look at the rehash function. It doesn't really take any parameters because we already have all the member variables of the hash map. We know we're going to double the capacity. At least that's the naive way to do it. More optimally, we could find the next prime number that's roughly double. So we're going to declare a temporary variable for our new map. It's going to be an empty array so far, but we want it to be of the size of the capacity that we're trying to do, which is roughly double the previous capacity. So we could do a loop for that. We could just append null to it to indicate that there aren't any actual pairs in this just yet. And then we're going to take our current map, our current member map, and assign it to a temporary variable old map. Then we're going to take our new map and then assign it to the member variable. So now our new map is the map that we're maintaining, but all we have to do now is take the values from the old map and then put them in the new map. So as we iterate through every pair in the old map, if that pair is non-null, we're just going to run the insert function or the put function that we talked about earlier, putting the key of this pair with the value of this pair. The reason we reset the size to be 0 is because we know internally this put function is going to be incrementing the size by 1 each time anyway. So that will give us the correct size. So that's why we reset this to 1 here. So these are the main ideas I wanted to talk about. You don't have to focus so much on memorizing every detail, just understanding the main concepts behind collisions, rehashing, increasing the size to minimize collisions, having some kind of intelligent hashing function where we also minimize collisions, having the size be prime also helps to minimize collisions. These are the important concepts to understand when it comes to hash maps. And even more important than that is just understanding how to use hash maps and hash sets, which we talked about earlier. We didn't talk too much about the details behind why inserting, removing, and searching runs in O of 1 time on average. The analysis could get complicated, and I don't think it's super important to understand. It's pretty safe to assume that those operations run in O of 1 time. That's what most people do, and to be honest, most people don't even understand what we've discussed so far. So if you understand even half of this, you're far ahead of most people.